Welcome again, and we will start from the place where we left off, which was basically making a harmonic approximation. But before I go into this one, something that I should have actually mentioned earlier was that in the case of transverse modes, so the displacements will be of a different type. The displacements will be, okay, let me just draw the picture and then tell you. So, if at this atom, if in the transverse direction it moves up, this one also moves up, this one also moves up, this also moves up, all by the same amount. So, this means translation of the crystal. So, again it has no impact on the internal energy of the crystal, and so nothing changes. But supposing I have a motion which is different, okay, so let me take the motion in the following way. Okay, so this one moves up, this one moves down, this one moves up, this one moves down, moves up, moves down, moves up, moves down and moves up. Then this is actually a k equal to pi by a mode, and it is transverse, and it actually corresponds to bending of the bonds, corresponds to bond bending, because for example, you know, this bond that is there here, after this motion it will look in the following way. So this will go up, this will come down, this will go up. So this bond has bent. Okay. So when you bend the bond, the energies bending, the bending modes in molecules have lower frequencies or lower energies than stretching modes. So which means that the transverse mode dispersion will be below the longitudinal mode. Okay, so now let us come to actually obtaining the form of the dispersion. So to get the form of the dispersion, let me look at the chain. So let me call this one as LH site, and this one as L minus 1, and this one as L plus 1. Okay. So let us say that the force constant of all the bonds, the near neighbor bonds, are same and given by capital K. Unfortunately, I use small k for the wave vector. If I had used q, this confusion would not have been there. So now the displacements at this site is UL minus 1, at this site is UL, and at this site is UL plus 1. So the change in bond length of the L minus 1 L bond is UL minus UL minus 1, and that of L plus 1 bond is UL plus 1 minus UL. Okay. So, let us look at the force on the Lth atom. The bond L minus 1 L has a force opposite that of L plus 1. Force exerts a force opposite to that of L plus 1 bond. So, the force constants are K. So, the force that is going to be there on the Lth side, Lth atom is going to be minus K UL minus UL minus 1 plus K UL plus 1 minus UL. So, this force is in one direction, this force is in the other direction, both of them are acting on the Lth side. So, this I can actually write it more compactly. So, I can write it as minus K times 2 UL minus of UL minus 1 minus of UL plus 1. Even this looks very similar to the time dependent Hamiltonian, time dependent Schrodinger equation. For the hydrogen atom chain. Okay, so, in that case what will happen is the following, that is, if I am looking at IH cross d psi by dt, where I will take psi to be the coefficients corresponding to the atomic orbitals, then I can write down the coefficient Cl by T is equal to H diagonal, which is LL times Cl minus of H L comma L plus 1 Cl plus 1 minus H of L minus 1 comma L Cl minus 1. So, this is the kind of equation that you will get there. I think you just have to express psi in terms of sigma over L Cl phi L and then plug it into IH cross sigma over L del Cl by del T phi L is equal to H operating upon sigma over L Cl phi L, then take inner product on both sides with say phi k, then you will get automatically the equation above with L being replaced by k. Okay, so this is very similar. I just wanted to show you how the vibrational problem is so similar in the way it looks, in the structure it is, because it is just a solid. So, because of the translational invariance, the two problems look very, very similar. Okay, now I have got let me go back to this equation, which is mu double dot L minus of k times 2 UL minus of UL minus 1 minus of UL plus 1, where double dot implies d squared ul by dt squared. So that mul dot is a force, and the force is actually given by the Hooke's law, or the spring, the force constant of the spring times the displacements. Now what I can do is I can say that ul I can say is going to be something like u e to the iql times e to the I omega, I should say k, not q, e to the I omega t. Let me take it as minus I omega t. So this can have a index uk because it is going with the vector k. So when I plug this into the equation of motion, then what I will get is the following: minus omega k squared m times uk e to the I k l a e to the minus I omega q t is equal to minus k times e to the I q l a 2 times e to the I q l a minus e to the I q L minus 1a minus e to the I q L plus 1a times uk e to the minus I omega q t. So now what I can do is I can actually cancel out some things. Okay, so I can cancel out uk e to the minus I omega t here and e to the I k l t to give me this, and only this part goes, this part goes. So just a minute, I am missing k and q, so this should be k on both sides, this should be k, this should be k, and this should also be k. Okay. So when I do this, I get minus omega m k squared m is equal to 2k times cos q cos k l a cos k a actually minus 1, because here the I q l a goes, k l a goes on both sides. So this is what I will get, and this one I can write as minus omega k squared, or I can write for omega k squared. I can write omega k squared is equal to 2k by m into 1 minus cos k a. So because it is a square, I might as well replace 1 minus cos k a by 2 sine squared k a by 2, so that I get omega k squared is equal to 4k by m sine squared k a by 2, or I would simply get omega k squared, omega k is equal to 2 times root k by m times modulus, I can put a modulus there, sine k a by 2. So you see that for small k, this behaves like this is capital K, this should be capital K. I have used Q, I made a mistake, but please be warned that this is capital K. So capital K is a force constant and small k is the wave vector. Well, unfortunately I have not used it consistently. So let me see whether there is any more place where I have actually messed up. So this should be capital K, okay, and this should also be capital K. this should be capital K, capital K, capital K. Okay. So, I guess I have covered all the places. So, omega k will go as 2 times root k by m into sin k by ka by t 2. If I expand it, it will go as ka by 2 is the first term. Okay. So, for small k I can just keep the first term. So, in which case I will get omega k is equal to root k by m times root k by m times k a. So, this dispersion is interesting. It is linear at very low values of k. So, I can say that this goes as is linear at small values of k. And what happens at when k is equal to pi by a, then what I will get is the following: omega k is equal to 2 times root capital K by m times sin pi by a into a by 2, or this gives me 2 times root k by m. So, you see that the dispersion should look something like this. So, there is a linear dispersion at k equal to 0, that is in the neighborhood of k is equal to 0, and saturates. So, this goes as 2 times root k by m. So, this value if I want to look at the velocity, the group velocity is d omega k by dk is equal to root k by m times a. Okay. So, this group velocity is much like dispersion of the sound waves. In a continuum. So, if you actually go back here and you see that it is nothing but a sound wave really. The reason why I say that it is a sound wave is because, see, all the atoms are, you are actually creating a density wave, because the density is changing as the chain oscillates, and density waves are nothing but sound waves. Okay. So, it is the densities that are oscillating, and so you have a sound wave. Okay. And that is why this is called acoustic branch. And when I am looking at the transverse modes, the transverse modes will go like this. This is the longitudinal mode, and the transverse mode will go like this. There will be 2 of those transverse modes. So, this is 2 degenerate transverse modes. Now, let us see what happens when we have 2 atoms per unit cell. So, let us assume for simplicity that the force constant remains the same, but only masses change. So you have one of small mass m, another one capital M. Okay. So these are the two masses that we have, and the chain will be consisting of small mass, big mass, small mass, big mass, small mass, big mass. So this is the chain that I have. Okay. So what are the kinds of motions that we can think of? So let me draw the unit cells as before. So I have a small mass, a big mass, a small mass, a big mass. Now what can happen is, let me try to illustrate it using transverse modes. The same thing holds for longitudinal modes, because transverse modes are easier to draw when in the plane of the paper. So when I am looking at it, what can happen is that both the atoms can be moving up. So for example, the q equal to 0, from now on I will use q, I will not use k because k is too confusing when I also have the force constant symbol as k. Okay, so what will happen is, in this case, for the q is equal to 0, both of them will move up. You can have both moving up. Within the unit cell and between the unit cells. Okay, so this is one possible mode that I can have, but within the unit cell there is no reason why the two atoms should be moving in the same direction. They can be moving in opposite directions as well. So if they are moving in opposite directions, then it will happen this way, that is, this moves up, this moves down, and this moves up, this moves down, 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 and this moves up, this moves down, this moves up, this moves down. So what you are seeing is that in both the modes, atoms with mass m move in the same direction by the same amount. This is the q equal to 0 mode, by the same amount. So also the atoms with mass capital M. So you are seeing here, see for example, this is moving up, this is moving up by the same amount everywhere. Okay. Here the small mass is moving up by the same amount everywhere in all the unit cells, and the big mass is moving down by the same amount in all the unit cells. Okay, so that is what is happening. Now you see that when atoms are moved by the same amount in the same direction, then you have the acoustic modes and there is no energy change. Okay, when atoms move in the same direction, by same amount, in each unit cell, there is no change in energy. But on the other hand, look at the other mode. So in this case you expect omega q equal to 0. When you look at the other mode, which is the mode here, you see that within the unit cell the small atom is moving up, the big atom is moving down. So in a way, within the unit cell, each pair of small m and capital M are actually performing a vibration, okay, because it is going up and down, going down and up and down and up by the same amount. So there is in the second mode, within the unit cell, m and m, small m and capital M, are moving in opposite directions. This is much like a vibration. Okay, so it is vibration within the unit cell, except that the vibrations in each unit cell have exactly the same amplitude and same frequency throughout the crystal. So that is what is happening in this case. So if that happens, then we have the frequency will not be 0, because the atoms are moving against each other. So they are moving against the bond. Okay, when they are moving against the bond, then there is a Hooke's law comes into place for play, and then you have a energy associated with the motion. The frequency is not 0, and you have omega k equal to some omega naught. Okay, so at k equal to 0. So this I will call it the optic branch, and this one where the frequency goes to 0, this I call the acoustic branch. So this is what is called the optic branch, and this is called the acoustic branch. So we know that the two branches that we have, if I am looking at k equal to 0 or q equal to 0, so I have one frequency here of one branch and another frequency there. So this is the optic and this is the acoustic. Now what happens when I go to q is equal to pi by 2a? When I go to q is equal to pi by 2a, the motions will be like this. Has a small mass, the big mass. So in this unit cell it goes up and this also goes up. In the next unit cell this goes down and this goes down, and same here, goes up, goes up, goes down, goes down, goes up, goes up, goes down, goes down, goes up, goes up. So, what you are seeing is that the direction of motion of a specific type of atom which is small, it is going up and down in alternate unit cells, or the large ones are also going up and down in alternate unit cells. Okay. So, the motion is the same with both the atoms within the unit cell moving the same direction, okay, but from cell to cell the phase has changed. So, this is also an acoustic mode, because within the unit cell atoms are moving in the same direction. And this is equal to q equal to pi by a, pi by 2a, let me call it, because let us say that the unit cell constant is 2a. Okay. So, that makes life a bit simpler when we want to compare with something else later on. So, now let me look at the optic mode, how it will look like. Okay, in the optic mode, this will move up, this will move down, and this will move down, this will move up, this will move up, this will move down, this will move down, this is move up, this will move up, this will move down, this will move down, this will move up, this will move up, this will move down. So, what we are seeing here is that between unit cells, okay, in successive unit cells, the motion of both the small atom and the large atom, large mass atom and the small mass atom, are switching the direction of motion from one unit cell to the other. And within the unit cell also, M and M move in opposite directions. So, that means that I still have q equal to pi by a, but the frequency will be different. You see, even here the frequency will be non-zero, because on this bond, which is 2 unit cells, 2 distance apart, the atoms are moving in opposite directions. So, there is some kind of a bending here, okay, and same here, there is a bending of this one, but within the unit cell there is no interaction, okay, that is in the sense both the atoms are moving in the same direction. So, there is no change. Okay. So, here omega acoustic at pi by a is non-zero, and here also omega optic at pi by a is non-zero. Okay, I will stop at this point, and in the next lecture I will continue from this point and then show you the equivalence between 2 atoms per unit cell that we are looking at here in the chain, and the Piles instability or the Piles distortion that one comes across in the case of the hydrogen chain, where you alternately make the hydrogen distances short and long. So, here it is very similar to that one, and I will show you how the two are actually equivalent, because the whole thing is something like nothing but dictated by the translational symmetry of the crystal. So, it does not matter whether you are looking at movement of atoms or the wave functions of electrons. So, that is what I want to emphasize. Thank you, and then we will see again in the next lecture. Thank you very much. Bye.